In this lecture, we'll be talking about Pavlovian conditioning. That is, we'll be covering classical conditioning, the variables that affect conditioning, and the theories of Pavlovian conditioning, or why we think it happens. We begin by talking about Ivan Pavlov. He was a physiologist. He was interested in studying digestion. Of course, the first step in studying digestion is studying salivation. And he thought that salivation was a reflex and that would be elicited by basically putting things in a dog's mouth. And so in order to study this reflex, he needed to collect saliva, and he developed surgical procedures so that he could measure the salivary response very carefully. And for his work, he won the Nobel Prize in 1904. The interesting thing is, or at least for us as psychologists, the interesting thing that he did is that while conducting his research, he noticed that his dogs began to salivate before he fed them. Now, for anyone who has a pet dog, this is not a surprising fact, but for someone who is doing research and for a scientist who's trying to very carefully study a salivary response, this is a problem. If the dogs start to salivate before he gives them food, then it's messing up his measurements of the amount of saliva that they're producing when they are given food. So he came to a point where he was trying to figure out what to do, and lucky for us, for psychology, he pursued this interest and pursued this problem that he referred to as psychic secretions. So, what Pavlov concluded is that there are two types of reflexes. The first type is the unconditional reflex. That's the one that we talked about in Chapter 1, or in the previous module. The one that is relatively permanent, it's hereditary, it's the basic reflex, the relationship between a stimulus and a response. So in this case, when the dog eats, it salivates. The second type of reflex, Pavlov called a conditional reflex. This is one that is learned, meaning that it's acquired and lost through experience. Because it's based on experience, it varies across members of the species. A dog with experience of hearing a bell prior to being given food may come to salivate when it hears the bell, whereas dogs without that experience will not show that reflex. Also, because it depends on experience, that means it's also temporary. So, further on about these unconditional and conditional reflexes, the conditional reflex can be broken up, and we can look at it in terms of it being a relationship between an unconditioned stimulus and an unconditioned response, or abbreviated as US and UR, with the US eliciting the UR. So again, this is the same as the reflex that we talked about in the previous module. All we've done now is defined it as being the unconditioned stimulus and unconditioned response, or the relationship being the unconditioned reflex. In the example with Pavlov's dogs, food would be the unconditioned stimulus, and salivation the unconditioned response. The conditional reflex is abbreviated as the CS and the CR, or the relationship between the conditioned stimulus and the conditioned response. So in the example with Pavlov's dogs, it might be the sound, a metronome, that then elicits salivation. What is the process of classical conditioning? Essentially what we're doing is we're pairing a neutral stimulus, one that doesn't elicit any particular response, and pairing it with an unconditional stimulus. So we start with something like the metronome that Pavlov used, tick, tick, tick. When he presents that to the dog does not salivate, doesn't do anything in particular. But if he gives the dog food, the dog does salivate. So the metronome is the neutral stimulus, the NS, food is the unconditioned stimulus, the US, and salivation, the unconditioned response, the UR. Next, we pair the neutral stimulus with the US, the food. So in this case, then we have tick, 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 and then he feeds the dog, and of course the food elicits the unconditioned response of salivation. We continue this pairing. So now, rather than refer to the metronome as a neutral stimulus as we did the first time it was paired, after it's been paired one time, we now refer to it as a conditioned stimulus, a CS. But we're still talking about the same stimulus. So the CS, the metronome, is then paired with food repeatedly until eventually presenting the metronome, presenting the CS, elicits a response by itself. At this point, then, the metronome would elicit salivation in the dog. To see another example of this, you can pause the presentation and play this video. And when the video is over, please resume the presentation. There are two really important notes. These are critically important to understanding Pavlovian conditioning. The first, stimuli are paired together and they're independent of anything that the subject is doing. All right? Regardless of what the participant, the subject, is doing, these stimuli are paired at them. All right, so in the example on the previous slide of the roommates, David, the experimenter, paired the sound effect with shooting his roommate. The pain, essentially, right? So it didn't matter what his roommate Brian was doing. If he was studying, if he was taking a nap, if he was just listening to music, playing video games, it didn't matter. All that mattered was that the sound effect was paired with the being hit by the pellet, right? Those stimuli were happening at Brian. Next, the other important note is that this behavior is a reflex. This is reflexive behavior. That means it's simple, involuntary reactions to a stimulus. These are not thoughtful responses. These are involuntary responses, right? So we're talking about simple behaviors, muscular jerks, glandular secretions that are being elicited by a stimulus. This next section covers the measurement of Pavlovian conditioning. So there are two different parts to this measurement. The first part to this measurement is, how do we know if conditioning has occurred? Well, what we can look at is, when does the response occur? So the latency between the presentation of the CS and when the response happens. So using the formula here on the side, we see that we have the CS turn on, the CS turns off. There's a little bit of time represented by the dash, 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 and then the US is presented, and it elicits an unconditioned response. If the conditioned response occurs prior to the presentation of the unconditioned stimulus, then that is evidence of classical conditioning, that conditioning has occurred. So if you think about it like this, that the CS is the metronome and the US is food, then if the metronome ticks and the dog salivates before the food is presented, then that is evidence that conditioning has occurred. The other way we can test to see whether conditioning has occurred is use test trials. In this case, then, we have a standard presentation where we present the CS followed by the US, but then we have a test trial in which we present the CS by itself. So present only the metronome and see if the dog salivates in the absence of food. If so, then that is evidence that conditioning has occurred. What are the types of dependent measures that are used for Pavlovian conditioning? So what are the things that are measured? Well, we look at intensity, so the amplitude or magnitude of the response, how strong is the response, or how much is secreted if we're talking about a glandular response. Basically, in order the way we might represent the strength, aside from using graphs, but if we're, as I talk and use these examples with just abbreviations, if I use bold letters like that, the bold CR, then that suggests that it's a strong conditioned response, whereas if I use lowercase, then that's a weak conditioned response. Generally, a stronger response is thought to represent more learning. The other measure is latency, or response time. We look at the interval between when the CS is presented and the conditioned response occurs. So essentially we're just looking at the time between the presentation of the CS and the occurrence of the behavior. And by looking at these things, we're looking for changes in behavior, changes in intensity, changes in response time. Remember that learning is a change in behavior. Now that we've covered basic Pavlovian conditioning, let's look at higher order conditioning. Higher or second order conditioning is when you pair a neutral stimulus not with an unconditioned stimulus, but with a conditioned stimulus, and that neutral stimulus comes to elicit a conditioned response. It will help, of course, to go through an example, which we will. So we begin by already having a conditioned reflex, a conditioned stimulus that elicits a conditioned response. So, for example, a light turning on that elicits salivation in a dog. Why would the light elicit salivation? Because it's already been paired with food before. All right, but now we have a light that elicits salivation. And we may have a neutral stimulus, such as a bell ringing. The bell is a neutral stimulus that does not elicit salivation. With higher order conditioning, what we're going to do is pair this neutral stimulus with a conditioned stimulus. So, for example, we'd be pairing the bell with the light. The light, being a conditioned stimulus, elicits a conditioned response in the dog. Just like before, after we've presented the neutral stimulus once we've paired it, it's no longer referred to as a neutral stimulus, it's now referred to as a conditioned stimulus. Here we'll refer to it as conditioned stimulus 2. And we continue engaging in this pairing of stimuli, CS2 with CS1. And as we continue to do that, eventually we can present CS2, the bell, by itself, and it too will elicit salivation. Now this is an interesting phenomenon. Interesting, I think, because the bell has never preceded food delivery. The dog salivating to a bell, but it has never gotten food after hearing the bell. And yet, because of the pairing of the bell with the light, the dog begins to react to the bell as it does to the light. So think about that. How does this discovery, the discovery of higher order conditioning, affect the importance of Pavlovian conditioning? In other words, does it impact how it might generalize or be useful in other realms? The next slide will get at that. Think about words. Think about the power of words. Think about the emotional power of words. Some words don't have a whole lot of emotional power. They have meaning, but they don't necessarily impact us in an emotional way. But some words do. Why? Why do they? And how is it that some words can have a really strong emotional meaning, and some words might have started off not having one, but then can have one later? This question was addressed by Stats and Stats way back in 1957. What they did is they showed participants nonsense syllables. All right, so some examples of these syllables are listed here: YOF, LAJ, QUG, etc. Right, so these are syllables that don't have any meaning. The participants were instructed to repeat a word that was spoken by the experimenter. So they would see the syllable, one of these syllables, and the experimenter would say a word, and the participant was instructed to repeat the word that the experimenter said. So, for example, they might see the nonsense syllable YOF, hear the word win, and then they would repeat the word win. And they were instructed that they were going to need to remember all of the words that they heard. They were told that it was a memory task. Try to remember all of the words that you heard. The words that the experimenters used, though, had either a positive emotional meaning, like beauty, friend, rich, success, money, win, or a negative meaning, like thief, bitter, sick, poison, fear, sour, evil, or a neutral meaning, so car, pen, key, etc., things that don't have emotional impact. So, in other words, participants may have seen then on the next trial XEH and then heard the word ugly and then had to repeat the word ugly. Every time one of the nonsense syllables came up, it would get followed with a different word. So when YOF was shown, they might hear the word win on one trial. The next time it came up, they would hear the word friend. The next time it came up, they would hear the word success, etc. When XEH came up, they would hear the word ugly one time, and the next time it came up, they'd hear the word bitter, etc. So they weren't just, in other words, they weren't trying to teach the subjects that XEH means ugly. They were just pairing XEH with negative emotional words. All right. At the end of all of this, they gave participants a scale and asked them to rate the syllables in terms of their pleasantness. And so they just had a Likert scale where 1 was unpleasant, 7 was very pleasant, and they had to rate these syllables. So here we're seeing the results of this pairing. Participants rated the words that were paired with positive emotive words like beauty, friend, gift, etc. They rated them as more pleasant than the syllables that were paired with the negative words. Keep in mind that they also asked participants if they noticed any sort of relationship between the nonsense syllables and the words that they heard. And any participant who said that they did notice, their data was thrown out of the study. So this is from the results only of those participants who did not detect any relationship. In other words, this is an unconscious conditioning. So, what does this tell us? This tells us that higher order conditioning plays a role in the emotional meaning of words. The words that we use, the words that we hear, when we have that gut reaction, this is why we have that reaction. What are the variables that affect whether Pavlovian conditioning occurs? So what are the things that impact its effectiveness? First, we need to look at the procedure itself. So you can refer to your text on these things as well, but essentially what we're looking at here are basic procedures. The trace procedure, if we look at time going from left to right, And each one of these blocks, so the red block with CS in it, what that means is that the CS is turning on the left side of the block and turning off on the right side of that block. And the US is turning on the left side of the blue block and turning off on the right side of the blue block. So what that means is that under trace conditioning, we have the CS turning on, turning off, then there's a delay, and then the US is presented, turns on, turns off. Under backward conditioning, well, it's just the opposite of that. The US is presented and is followed by the CS. With simultaneous conditioning, the CS and the US turn on and turn off simultaneously. And under delayed conditioning, the CS turns on, and while it's still on, the US is presented. So, which of these do you think would be the most and least effective? As it turns out, the trace conditioning and delayed conditioning are both very effective, depending on some things that we'll talk about shortly. Backward conditioning can work, but not in the way that we've been talking about. And the least effective of all is simultaneous conditioning. Presenting the two together results in very little, if any, change in behavior. So, now we get to some terms that were going to follow us through the rest of the semester. And contiguity is the first one of these. Contiguity is nearness in time or space. When things are contiguous, that means they are close together. High contiguity means that they are very close together. In the case of Pavlovian conditioning, what we're really talking about is how close things are together in time. In other words, how close is the CS to the US? This measurement is referred to as the interstimulus interval, or the ISI. So let's look at examples of our conditioning procedures here. In trace conditioning, we have the CS preceding the US, with a delay in between. With delayed conditioning, the CS precedes the US, but they overlap. There is no delay in between. How do we measure the interstimulus interval? In the case of trace conditioning, well, that's relatively straightforward, right? We just look at how long is the delay. And so we measure the time between when the CS turns off and the US turns on. In the case of delayed conditioning, we measure the time between when the CS turns on and the US turns on. In general, the shorter the interstimulus interval, the faster conditioning will occur. In general. There are, of course, limitations on that. If the interstimulus interval is 0, then that is simultaneous conditioning, and no conditioning occurs in those situations. The other term that is going to follow us throughout the rest of the semester is contingency. Now, what is a contingency? Contingency is essentially a rule of if this, then that. And in the case of Pavlovian conditioning, this rule is if the CS occurs, then the US occurs. In other words, it comes down to prediction, that if the CS happens, then the US will happen too. If a metronome ticks, then food will be given. That kind of thing. So one of the early questions that came up in Pavlovian conditioning was it just a matter of the number of times that a CS and US were paired together? Is that what constituted or was necessary for learning? Or was there more to it than that? And so Robert Rescorla tested whether the contingency the prediction of the CS to the US, whether that was important or whether it was just number of pairings. So he tested this by having 3 different groups of rats. All of them got the same number of CS-US pairings. So he kept the number of pairings constant, but he manipulated the contingency. So what does this look like? The high contingency, medium contingency, and low contingency groups of rats all had 10 CS-US pairings. They all had the same number of pairings. All right? So there was no differences there between the groups. What did differ, though, is that while they were getting these pairings, the high contingency group never experienced the US by itself. So they got 0 times that the US occurred without the CS happening before. In other words, every time they experienced the US, it was always preceded by the CS. For the medium contingency group, though, a couple of times that they experienced the US, it wasn't preceded by the CS. So this would be like Pavlov feeding his dog without having the metronome going. Just a couple of times, right? And in the low contingency group, there were more occasions in which the US was presented without the CS. Now, what impact should this have? If all that matters is the number of pairings, then all 3 groups should have acquired the conditioned response to the same degree. But, as it turns out, those that were in the high contingency group acquired the conditioned response very strongly. Those in the medium and the low group, however, did not. So what this revealed is that it's not just how many times the CS and US are paired, but it also depends on whether the CS predicts the US. And the better the CS predicts the US, the better the conditioning will be. So that CS-US contingency is critically important. Other variables that affect whether conditioning will occur and how rapidly it will occur. Stimulus intensity. In general, the more intense the stimulus, whether we're talking about the CS or the US, the more rapid conditioning will occur. In other words, bright lights, loud noises, etc., will produce stronger conditioning than dim lights and quiet sounds. However, again, there are limits. If you use a stimulus that is incredibly intense, extremely intense, then that can interfere with learning. A bright light works, but if it gets too bright, then it hurts the eyes, and it can interfere. A sound paired with food delivery, like a bell ringing prior to food, that will work really well, unless the sound of the bell is so loud that it hurts the ears. In which case, the dog will react to the bell itself and be fearful of that because it produces pain, rather than learning about the bell being followed by food. The number of pairings does matter. Contingency is important, as we stated on the previous slide, but the number of pairings is also important. In general, more pairings produces stronger learning. On the graph, we're looking at the strength of the conditioned response on the y-axis, the number of pairings across the x-axis. And what we'll see is that as we increase the number of pairings, then the strength of the conditioned response will increase. And it does so in a non-linear fashion. We get a lot of learning early and less learning later. Remember, learning is defined as a change in behavior due to experience. So when I say more learning early, what I'm really saying is that there is a greater change in behavior in the first trials than there is in the later trials. So, for example, if we look at the change in the strength of the condition response over the first 8 trials, we see that we go from 0 condition response to a condition response of about 9 over those first 8 trials, right? So we've had a change in behavior on the order of 9 units. Over the next 8 trials, from 8 to 16, we see a change in behavior from 9 to about 13. So a change of, instead of a change of 9 units, a change of 4 units. So less change later, and if we were to continue that out, we would see less and less change as it goes on. So we're seeing more learning, more change early, less change later. Other variables that affect learning, these are organism variables, so these depend on the subject that is being conditioned. Age is an important factor. Looking at eye blink conditioning, so this is like kind of like a glaucoma test, a little eye puff into the eye, but with eye blink conditioning, there would be a light or a sound that would precede the eye puff, the puff of air, and we look at whether the eye blinks in response to that sound or light. Looking at children, young adults, and older adults, what we see is that the younger adults actually condition faster and stronger than the children or the older adults. So there's an impact of age on conditioning. There's an impact of temperament. As we know, individuals vary in their temperament. Some people are more excitable, right? They react strongly to little things. Other people are more sedate. It takes a stronger stimulus to excite them. Who do you think would condition faster? Maybe no surprise. Those who are more excitable condition faster than those who are more sedate. Keep in mind, this does not mean that one is more intelligent than the other. This isn't a question of intelligence. This is a question of classical conditioning alone. How rapidly their behavior will change in this reactive way to stimuli. Lastly, stress or anxiety. The more anxious one is, the more stress there is on someone, then the more likely they are, or the more rapidly they can be conditioned. Essentially, what the stress and anxiety does is it moves someone into a more excitable state. And that shows up in terms of how rapidly they will learn. This next section delves into some Pavlovian phenomena. So these are some kind of unique, interesting findings. They may get a little bit muddy as we go through. I'm trying really hard to make them be clear. You can read over these in the textbook as well, and that will help. But I'm trying to do this to help make the textbook more clear, but I would recommend using both sources. Here we go. The first phenomenon we'll talk about is called overshadowing. With overshadowing, we're looking at how a CS that has more than one component, more than one element, can have one of those elements be conditioned more effectively than another. So what does that mean? I realize that's confusing. So let's look at the procedure. First, what we're going to do is we're going to train a compound stimulus. So rather than it just being a light or a bell or something like that, it's going to be a combination of things. So it might be a light and a buzzer that turn on together and turn off together. All right. So we have essentially a noisy light or a bright sound. Right. These things they're turning on together, turning off together, and followed by an unconditioned stimulus, say meat. Right. And then the meat, being an unconditioned stimulus, elicits raindrops. I mean salivation. After that training, so we've trained with this compound stimulus, that means that the light and the buzzer have turned on together, turned off together, and been followed by the presentation of food the exact same number of times. What we'll then do is we're going to test the compound stimulus. So we present just the compound stimulus and we see that it elicits salivation, but then we can test each of the components separately. We can present just the sound and we can present just the light. With overshadowing, we find that when presenting only one of the components at a time, that one of the two will produce a stronger response than the other. In which case we would say that the buzzer, in this case, overshadowed the light. When the buzzer is presented by itself, we get a strong conditioned response. When the light is presented by itself, we get a weak conditioned response. This is an interesting phenomenon because both of them had the exact same contingency, contiguity, and number of pairings with the meat, right? But one of them conditions stronger than the other. Blocking is very similar to overshadowing and therefore easy to confuse, but there is a really important difference. This difference deals with how will previous experience affect these new pairings. So with blocking, we start out doing conditioning in the normal way. So we have a CS that's paired with a US, right? So we have this tone that is paired with an unconditioned stimulus of shock. This is what Kamen did in 1969. The unconditioned response to a pain stimulus like shock for a rat is that they freeze, they stop moving, right? So he did several pairings of tone followed by shock, tone, shock, and then introduced another stimulus as a compound. So when the tone came on, a light also came on. So the tone and the light turned on together and turned off together and were followed by shock. So in this case, we might expect then when we test these individually, what we might expect is that the tone would produce a stronger conditioned response than the light, simply because the tone had been paired with shock more times than the light had. But interestingly enough, what was found is that the tone produced a strong conditioned response and the light produced zero conditioned response. None. The previous experience with the tone blocked any learning with the light. So what blocking gets at is how previous experience with one of the components can interfere with or block learning when another component is added. Latent inhibition deals with the previous experience with a neutral stimulus. So in other words, if there's a stimulus that we have been exposed to, but it has not been paired with anything, how will that impact learning once it is paired with an unconditioned stimulus? So the experiment here, Loblow, 1965, using sheep, again pairing a tone with shock. In this case, it was a small shock to the flank of the sheep, which caused sheep to kind of kick. All right, so the kick is the conditioned response, the unconditioned response in this case. He has three different groups. One group never heard the tone before, so this is a tone that the first time they heard it is when it was followed by a shock to their flank. The second group of sheep heard the tone 20 times, so they're just, during their day, they're just hanging out, and this tone turns on and turns off. Nothing in particular happens. And the third group had that 40 times, that they heard the tone turn on, turn off, and nothing in particular happens. Then the tone was paired with shock for all of them. Right? And what we're looking at then is the strength of the conditioned response after the pairings began. Right? So I'll put the first one up here. So for the 0 group, we see that these are the ones that the first time they heard the tone, it was followed by a shock. And so we're looking at the strength of their conditioned response across days of training. And we see that it goes up. Like on the first day, they're already showing a conditioned response, and that only increases across the 4 days. What about the ones that have already had experience with the tone? Will that experience help them learn more quickly? Will it slow learning down? Or will it have no impact at all? As it turns out, those who had previous experience, who had heard the tone turn on and turn off 20 times before and it was never followed by shock, it took them longer to learn, and those that had heard it 40 times took them even longer to learn. So in other words, when the tone was presented without shock, essentially we might say that what the sheep were learning is that the tone was unimportant. It didn't predict anything. When the tone did start to predict something during the conditioning trials, then the sheep had to learn that this thing that never was important now is. And it took more trials for them to then overcome that. And that phenomenon is called latent inhibition. That previous exposure to a stimulus can interfere with conditioning. So the take-home then is that novel stimuli are the ones that are most easily conditioned. Sensory preconditioning, this is a fun one. How will previous pairings of two neutral stimuli affect later conditioning? I just got to say, check out the date on this, 1939. And for all of these phenomena, overshadowing, blocking, latent inhibition, sensory preconditioning, for any one of these you can do a Galileo search, a research search on these, and you can find articles that deal with them that are current, that have been published in the last year, because these things never go away. Like they are so reliable. Anyway, so what did Brogden do? Brogden started off by pairing a tone, a light and a tone. Right? Both of these are neutral stimuli. They didn't elicit anything. It's just light followed by a tone, and that's that. So light turns on, turns off, tone turns on, turns off, nothing else. This is with rats, by the way. So the light turns on, turns off, tone turns on, turns off, nothing else happens. Then the tone, so after that experience is over, then the tone was paired with shock. So the rats would be hanging out in their chamber, and the tone would turn on, and then the tone would be followed by a shock. The shock would produce a fear response, an unconditioned fear response, right? Until eventually, when the tone came on, then the rats had a conditioned fear response to the tone. They would freeze up. After all of that, Brogden then presented the light. And the question is, what effect did that have? And the answer is, the light produced a fear response. So that's the phenomenon of sensory preconditioning. That by pairing two neutral stimuli prior to anything else, right? You're just pairing a light and a tone, but then you take the tone and do conditioning with it, then you go back and present this light, and the things learned with the tone are also learned with the light. And this is fascinating because the light has never been paired with shock, and when the light was paired with tone, it was before tone had ever been paired with shock, and yet the light can turn on and the rats responded with a conditioned fear response. The last phenomenon we'll discuss is extinction. And so once a conditioned reflex is established, it can persist indefinitely, as long as we have pairings between the CS and US on occasion. So in other words, a dog can respond, can salivate to a bell, as long as the bell precedes food from time to time. But every time we present the CS by itself, it reduces the strength of the conditioned response. If you think about that, if we present a CS by itself, that means that we are breaking up the contingency between the CS and the US. We're breaking up the contiguity between the CS and the US, and the predictiveness, right, between the CS and the US. So every time we do that, it's called an extinction trial. So what Pavlov did is he had dogs that, of course, dogs generally before they eat food, they see food, which is why when dogs see food, they begin to salivate, which is why when we see food, we often also begin to salivate, because we generally see the food before we eat it. So what Pavlov did, though, is he showed dogs food, but did not let the dogs eat the food, and he measured the amount of saliva across these trials. So he did this 6 times, and he found that the amount of saliva produced when the dogs saw the food decreased across these 6 times until it essentially just went away. This procedure is called extinction. Keep in mind, though, extinction is not the same thing as forgetting. The dogs did not forget this conditioning. Forgetting is a different thing altogether. Forgetting is a change in behavior, a decrement in behavior over time without the ability to practice. That's a whole different issue that we'll get to later. This is learning. Extinction is learning. It's learning that the stimulus is no longer followed by the other stimulus. What's interesting, though, is that if after that extinction, so after those 6 trials, Pavlov then waited for a couple of hours and then showed the dogs the food again and measured their saliva. And he found that the dogs again salivated. Not as much as they did the first time, but that the response came back. This is known as spontaneous recovery. And this is a really important thing. What it means is that anytime extinction is used to remove a response, that response must be extinguished multiple times, which is really important when it comes to the treatment of phobias, for example. This brings us to the last section, theories of classical conditioning, attempts to understand why conditioning happens. We start with stimulus substitution theory. This is Pavlov's own theory. In this theory, Pavlov speculated that there's an area in the brain that is triggered when the US is detected, and that same area then triggers the unconditioned response. So if we look at the diagram, we see on the left a US, so the unconditioned stimulus. The tasting of food is detected somewhere in the brain, and then that area of the brain triggers the unconditioned response of salivation. All right, that's what that's saying. He also speculated that the CS activates another area of the brain. So when a metronome ticks, tick, 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 that stimulus is detected and activates some area of the brain, presumably in the auditory cortex. He then speculated that pairing the CS and the US produces connections between those brain areas. Essentially, it's the idea that things that fire together wire together, which is actually a really good idea that still is around today. But essentially, by activating the CS area of the brain and the US area of the brain, the connections between those grow, as represented by the red arrow on the diagram. What that leads to then is that the CS, when presented, it activates the CS area of the brain, which then in turn comes to activate the US area of the brain, which then triggers the conditioned response. So, consistent with the title of stimulus substitution theory, the idea is that the CS can substitute for the US. Now, what are the implications of this? What does that mean about the conditioned response and the unconditioned response? What it means is that since the unconditioned response is produced by the US area of the brain, and the conditioned response is produced by the US area of the brain, that those responses are exactly the same. The question is, are they exactly the same? Well, that's an empirical question. We can test that. And as it turns out, we have tested that, and they are not. Not always. Sometimes the conditioned response is the opposite of the unconditioned response. So, for example, when an animal is shocked, it produces a fear response, which is an increase in heart rate. However, if a tone is paired with shock, and the tone then produces a conditioned response, then when that tone comes on, we don't see an increase in heart rate. Instead, we see a decrease in heart rate. And the idea here is that what the conditioned response is doing is it's preparing the organism for the upcoming unconditioned stimulus. So, if we think about it, these unconditioned stimuli, food, shock, etc., these unconditioned stimuli are important events to the organism. And so the idea here is that the unconditioned, or the conditioned response is preparing the organism for the important event that's about to happen. So if the unconditioned stimulus is food, then the conditioned response of salivation is preparing the dog for the food that it's about to receive. Alright, so having bell followed by food, the bell elicits salivation in preparation for the food that's about to happen. If it's a tone that is followed by a shock, shock increases heart rate. When the tone comes on, the rat's heart rate decreases in preparation for the shock event that is going to increase its heart rate. The increase in heart rate is, of course, a challenge to the animal system. So by decreasing its heart rate first, it's preparing itself for that upcoming challenge. So these theories, both preparatory response theory and compensatory response theory, both of them are theories that argue that conditioned responses prepare the animal for the upcoming unconditioned stimulus and response. Essentially, the take-home, though, is that stimulus substitution theory has not been upheld. It's been ruled out. The last theory we'll talk about is the Rescorla-Wagner model. Now, models are theories, but theories with numbers, essentially. So, just like a theory, they're trying to describe a large set of data, observations, on the basis of just a few elements, and trying to make definite predictions about the results. The assumptions of the Rescorla-Wagner model are quite simple, actually. It assumes that there's a limited amount of learning that can occur, so a limited amount of change in behavior that can occur, and that the rate of learning is also limited. So what limits it? Well, it depends on what the stimuli are. The stronger the stimulus, the stronger the learning, remember. So it depends on the US, it depends on the CS as to what the amount of learning can be and what the rate of learning can be. It also assumes that every time the CS and US are paired, some learning occurs, some change in behavior occurs. So each trial gets the participant one step closer to its maximum level of learning, or 100%. All right. It also assumes then that each trial produces less learning than the last, which that just goes back to how we were describing the learning curve before, which is that we get more learning early, less learning later. So let's look at the model. Here is the model. It might look a little bit scary, but it's actually not too difficult. We'll walk through it. The delta Vn stands for the change in strength of the association on that trial. In other words, it's the amount of learning that occurs on any given trial, on any given pairing of CS and US. The C, this is a constant, so this is something that has to be figured out separately. Essentially, it depends on what the stimuli are that are being paired. So are we using a dim light and pairing that with a little bit of sugar, or are we pairing a bright light with a shock? Like, depending on what the stimuli are, the C value will change. And that has to be figured out, like I said, separately. There's a whole separate equation for that. Lambda represents the maximum amount of learning that can occur. For our purposes, we'll just call that 100%. 100% is the maximum amount. And then the last part here, Vn minus 1, that's the amount of learning that had occurred on the previous trial. So n being the current trial, n minus 1 being the previous trial. So with that in mind, let's walk through the calculations. Here's how we do these calculations. As we go through, I think you'll see it's not quite as complicated as it might sound. Trial number 1, we're trying to solve for the change in Vn, right? We're trying to calculate how much learning has occurred on that trial. I'm using 0.5 as the C value, 100 for lambda because that represents the maximum amount of learning. As far as the amount of learning that has occurred on previous trials, well, there was no previous trial, so 0 is the amount of learning that has occurred up to this point. And then we solve for that. 100 minus 0 times 0.5 equals 50. So on trial 1, the change in learning is 50. So we can plot that on the graph that on trial 0, the amount of learning was 0. On trial number 1, the amount of learning is 50. To calculate for trial number 2, we have the same C value of 0.5, the same maximum of 100, but the amount of learning that has occurred on the previous trial is 50. So now we do 100 minus 50 times 0.5 equals 25. So the amount of learning to occur on trial 2 is 25, and we add that onto our graph. On trial number 3, the only thing we have to change is the amount of learning that had occurred on previous trials. Instead of 50, it was 75. So now we have 100 minus 75 times 0.5 equals 12.5. And we just continue doing that from trial to trial and plotting it each time. And we see that it produces that negatively decelerating curve that is a standard learning curve. That we get more learning with every pairing, with every trial, but less learning each time. Now, what happens if we change the C value? The C value affects the rate of learning. So the c-value of 0.5 is what we just used, and we saw that it produced a learning curve that looked like that, the blue line here. But if we change the c-value, so if we were to increase it to 0.8, which by the way is very unrealistic, but if we were, then we would see a much sharper curve, faster learning, and if we reduce it to 0.25, then we see a more shallow curve, less learning on each trial. But all of them eventually will get very close to the maximum amount. So in summary, for the Rescorla-Wagner model, it has had a lot of successes. It can reproduce that negatively decelerating learning curve. It allows for one to predict learning. And it does a really good job of describing some of the Pavlovian phenomena that we've talked about, like blocking, for example. However, it does have some shortcomings. Calculating C, that constant, can be difficult. It essentially has to be done through conditioning. It can't be done any other way. And it doesn't successfully describe all of the Pavlovian phenomena. It doesn't do a very good job with latent inhibition, for example. Overall, though, it continues to be very influential. It drives debate and research, and just like the Pavlovian phenomena that I said before, if you look up Rescorla-Wagner model through a Galileo search or something like that, you'll find a ton of hits for it in current research. So even though it's been around a long time, it continues to be a very influential way of looking at and addressing conditioning. So, to summarize then this lecture, Pavlovian conditioning involves reflexes, simple involuntary reactions to stimuli, and it deals with stimulus-stimulus pairings, so CS and US pairings. Pavlovian conditioning establishes our reactions to things, right? So it's not only fear, but salivation and flinches, but also our emotions, our gut feelings, perhaps our biases and our prejudices too. The meaning of words, for example. And it can impact how we feel and react to people, products, places, songs, smells, all these different things. In other words, although a lot of the research with Pavlovian conditioning, and in particular Pavlov's original work, dealt with bells and dog spit, but it really is a much more important phenomena that is often recognized. And Pavlovian conditioning is a major part of why we do the things that we do.